Have you ever really thought about balance? I don't mean just in life, but as a pure mathematical law of the universe. Well, today we're diving into this incredibly elegant idea from geometry that does just that. It's called the Barycenter, and trust me, it's the secret to finding the perfect point of equilibrium in literally any system. Okay, think about a seesaw, right? If two people with the exact same weight sit at the same distance from the middle, it balances. Easy. But what happens if one person is twice as heavy? Intuitively, they have to shuffle closer to the center to make it work. The real question is, how do we find that exact spot every single time, no matter how complicated the setup is? That is the question the Barycenter was born to answer. So let's do it. How do we find this perfect balance point? Well, before we can start calculating, we've got to learn the language. We need to define the core ideas, the building blocks of this whole concept of equilibrium. First things first, the weighted point. This is a super simple but really powerful idea. See, it's not just a dot in space. It's a point that has a certain amount of mass or influence attached to it. On our seesaw, it's not just where you sit, it's also how much you weigh. This combo, a point and its weight, is the absolute foundation for everything we're about to build. Now, how do we measure the balance of a whole system of these weighted points? Well, mathematicians came up with this brilliant tool. You can think of it like a balance detector. You pick any spot in space, let's call it M, and this function calculates the total combined pull from all the weighted points. It spits out a result that tells you two things: the direction of the pull and how strong that pull is. That right there is what we call a vector. So what happens when our balance detector reads 0? That's the magic moment. The Barycenter, we'll call it G, is the one single unique point in the entire system where the combined pull is nothing, 0. It's the spot where all the weighted pulls, all the different influences from every single direction just perfectly cancel each other out. It is, quite literally, the mathematical point of perfect balance. Okay, so we've got our definition of the balance point. But what makes this concept so incredibly useful are the simple, almost shockingly powerful rules that govern it. Let's take a look at what are basically its superpowers. These properties are like cheat codes for geometry. First, it doesn't matter what order you look at the points in. The balance point is always going to be in the same place. Second, you can multiply all the weights by 5 or 10 or 1,000,000. And guess what? The Barycenter doesn't move an inch. And third, and this one is the real game changer, is something called associativity. It means you can take a super complicated system, find the Barycenter of just a small chunk of it, and then replace that whole chunk with their single Barycenter. This lets you break down massive problems into tiny, easy steps. And here's that scaling property in action. Look at System 1 on the left. Point B has twice the weight of Point A. Now, in System 2, we've multiplied both of those weights by 5, but the ratio is still 2 to 1. And notice, the balance point, G, is in the exact same spot for both. This proves it. It's the relative influence that matters, not the absolute numbers. All right, the theory is cool, the rules are powerful, but how do we actually find the Barycenter when we have 3, 4, or even 100 points? Let's walk through how to actually build it. This is where that superpower of associativity really shines. It makes building these things incredibly simple. Say you have a 3-point system. You just ignore the third point for a minute. Find the Barycenter of the first two. We'll call it G1. Now, this new point G1 basically becomes a single point with the combined weight of the first two. And finally, you just find the Barycenter between that new point, G1, and the third point you were ignoring. And that's it. That's the final balance point, G. You can just keep repeating this process for any number of points. It's that easy. But the Barycenter is way more than just a method for finding a single point. It's so fundamental that it gives us a completely new way to map out space itself, describing the entire world through the lens of balance. And this isn't just some abstract idea. It's the foundation for really practical things, like 3D computer graphics. So ask yourself this crazy question. What if we could describe the location of any point in a plane, not by its x and y coordinates, but by a unique set of weights that would make it the balance point of 3 fixed reference points, like the corners of a triangle? Well, that's exactly what barycentric coordinates are. It's a completely different address system for space. Instead of saying go 3 units right and 2 units up, you say apply this much influence to point A, this much to B, and this much to C, and the balance point will land you exactly where you need to be. It's incredible, and it's literally how a computer knows how to shade a triangle in a video game, blending the colors perfectly from one corner to the others. But there's a little catch. Remember that scaling property? Since we can multiply all the weights by any number and still get the same barycenter, it means there are infinite addresses for the same point. And an address system isn't very useful if one house has a million different street names, right? We need a way to make it unique. And here is the absolutely elegant solution. We just add one simple rule. The sum of all the weights must equal 1. That's it. By adding that single constraint, boom, suddenly every single point in space has one and only one set of barycentric coordinates. It just snaps the entire system into this perfectly unique and incredibly useful map of space. Okay, let's zoom out for the big picture. This whole idea of balance goes way beyond just finding a point. It actually helps us understand the very nature of shapes and spaces, taking us from vectors all the way to simple numbers or scalars. Remember our balance detector from before, the one that gave us a direction and a strength? Think of it like a compass pointing in the direction of the imbalance. Well, it has a cousin. This other function doesn't care about direction at all. It just gives you a single number, a total strain score for any given point. The further you are from the points with the most weight, the higher your strain score is. So it's not a compass, it's more like a pressure gauge. All right, let's switch gears for just a second and talk about shapes. A convex set is basically any shape that doesn't have any dents in it. A circle is convex, a square is convex, but a star shape? Nope, that's not convex because you can draw a straight line between two of its points and part of that line will fall outside the star. And here is the ultimate connection, where it all just clicks together. What on earth does the shape of an object have to do with the seesaw? Turns out, everything. A shape is convex, it has no dents, if and only if it always contains the balance point of any combination of points you pick inside it. It's this profound link. A purely geometric property is perfectly and completely described by the physical concept of balance. This simple statement here is actually a super powerful and universal test. How can you tell if any shape, no matter how weird or complex, is convex? You just have to answer one question. Does it always contain its own center of balance? If the balance point of any points you pick inside it always lands back inside the shape, then it's convex. It's a beautiful, self-contained definition. And this leaves us with a pretty fascinating final thought. We started with a simple seesaw, and we ended up defining the very nature of shapes through this idea of balance. It really makes you wonder, in math, and maybe everywhere else, what does it truly mean for a system to be able to always contain its own point of equilibrium?